Welcome to Tidslinjen Podcast. Don't forget to subscribe.
And I would start with saying a warm welcome to Dr. Murtazo Nazarov. Welcome to the show. It's really nice to have you here. So welcome.
Yeah, thank you so much. Thank you for the invitation. I'm very glad to be here.
Yeah, it's going to be really exciting because it's a subject that I've been actually reading about for a long time, and it's fusion. It's a thing that is very interesting and a process that's happening in the sun all the time. And it's something that we want to recreate somehow on Earth to have access to limitless energy. But it's so much more than that. But before we jump in on all that fun stuff, I think it's important for the people who's listening or watching to get to know your background and your research and who you are.
Yeah. Originally, I am from Tajikistan. I did my education, undergrad and master education in Tajikistan in pure mathematics. Then around 20 years ago, I moved to Sweden to do my master degree in computational science, because in Tajikistan, we don't have this kind of subject, computational science. I came to Sweden. I did my master at KTH, computational science. Then I did my PhD there. The same subject, numerical analysis, computational science. Then I moved to Texas to do my postdoc, and I worked here for 3 years, and we decided to get back to Sweden, and since then I work in Uppsala now.
Okay, Uppsala University.
Uppsala University, and I am associate professor in the division of scientific computing.
Cool. What a journey you have done.
Education was my passion, so I was moving from one place to another place. I've been several times in Russia in the past, also several universities in the US. I found it really interesting to find and talk with very interesting people and gain knowledge and try to solve something which is related to the real life and not something abstract.
No, it's really cool because we're lucky to have scientists like you to solve problems. If it was up to us normal people, we would still use wood and fire to make energy. So it's really good to have people like you. So we really appreciate it.
Yeah, thank you.
So to the subject we will talk about today, fusion. Maybe we should start by talking about what fusion is. So could you give us an introduction to fusion?
Yeah, so fusion, as you said in the beginning, it's a process that is happening on all the stars and including our sun. For example, if you see the surface of the sun, the fusion reaction always happens, and in this reaction, two atoms, deuterium and tritium, if you don't want to go into these technical details, they join and they become helium and some neutrons, and they release enormous amount of energy. And all this energy that we get from the sun is actually the result of this fusion process. So the idea that people started to think, can we recreate this reaction that is happening on the surface of the sun? And that's why all this fusion direction and all these researchers that they are trying to solve this problem, it's actually they are dealing with this issue. How to create the reaction that is happening on the surface of the sun on Earth.
It's not an easy challenge to accomplish, I can imagine.
Yeah.
But what is the main difference from what we are doing today in fission, where we split atoms? So what is a bit the difference there with fusion?
Yeah, so the main difference in fission, the atoms split by small particles, and during the splitting, they generate a lot of energy. So the problem is the good thing is fission is well understood, more or less well understood. We have nuclear reactors, we have nuclear power plants. We produce nowadays about 10% of all the energy that we created. It comes from nuclear fission. But the problem is, since it always splits, this process goes for thousands of years. And during this splitting, it creates a lot of radiations. And after some times, we gain energy. And the technology that we have it now, they don't have an ability to harvest energy from all this splitting. So what we do, we say that, this fission is done, and we take it and we put it under the ground. So we store it for thousands of years. And this is very dangerous, and because of this radioactivity, if there is an earthquake, they can erupt. But in fusion, the process is opposite. Instead of splitting atoms, we join atoms. So we create this environment that fusion happens. When the fusion happens, these two atoms, they get one atom, and the result becomes sometimes I tell it to my students when they ask this question. So how do we get this energy? I say we have 1 kilo of hydrogen, another kilo of hydrogen. So we join. What does it becomes? So it becomes helium, so two atoms. And I say how many kilos would be the result? So they say 2 kilos. But in reality, it's not 2 kilos. It's 1.5 kilos of helium. The other half kilo, it becomes transformed to energy. Mm-hmm. So the idea is in fusion, since the atoms join and we don't have this radioactivity, and this process is very safe, it's not hazardous, and there is no explosion, for example. Sometimes it happens in fission reaction. So it is opposite.
Okay. And what fuel are we using? You mentioned hydrogen. In fission, we use uranium. And what's the fuel for fusion?
For fusion, the fuel is water. So we need deuterium and tritium. Mm-hmm. So deuterium, we can find it in seawater. And if you ask me how many fuel we have, it's almost infinite, because we have so many oceans and all this process will be repeated. And but tritium is a bit hard to harvest it or collect it, because tritium, we can get it from lithium, this battery stuff. But the good thing is when we create successfully fusion reactors, so tritium will be generated during the process. So think about that. We have deuterium, which is unlimited, and tritium will be generated during the fusion process. Okay. And because of that, fuel for fusion, it's almost unlimited. If we succeed generating energy from fusion, it's going to be something breakthrough.
Okay. And there's basically no waste like there is in fission.
There is almost no waste. I say almost, because when the reaction happens, some neutrons, they fly away. So these neutrons, they hit the wall of the reactors. They produce some radioactivity. But the radioactivity that these neutrons generate, it dies very quickly. So it's not for thousands of years. It's not super radioactive. I mean, if we store it in some place, it's going to be, in a few years, it will be just completely radioactiveless. So, but in fission, we repeated that it's opposite.
Okay. But now maybe we're going into details, but I like going into details as well. But what are the practical challenges that we face today with the fusion reactors, for example? Because what I know, there's not a fusion reactor working commercially today.
Yeah, that's a very good question, because if we want to create fusion reaction on the Earth, we have to mimic or recreate the condition on the surface of the sun. And what are the conditions on the surface of the sun? For example, since the mass of the sun is really big, the pressure is super high. So either we have to create a condition that the pressure is so high that when we put this deuterium and tritium, so they fuse. And also, of course, the surface of the sun, the temperature is around 6,000-7,000 degrees. It's easy to create it on the Earth. So either we create really high pressure with this 6,000 or 7,000 degrees of Celsius temperature, or we do opposite. We do really high temperature, because on the Earth, it's really hard to create this pressure condition, which is, we have it on the surface of the sun. So the other way is, instead of creating this pressure, we can increase the temperature. So what we have, like for this current fusion reactors that we have, the condition should be, the temperature should be 150 million degrees of Celsius.
150 million
degrees of Celsius. And if you think like the core temperature of the sun, so this sun's core temperature is like 15 million degrees of Celsius. So we have to create 10 times more than the temperature of the sun.
Wow.
And only in that situation we can get this fusion reaction. Otherwise, reaction will not happen. So
well, how can we even manage those temperatures on Earth? How can we create 150 million degrees Celsius? Is it possible?
It is possible. So the easy question, of course, there is a lot of technical stuff to explain it, but I can, when I tell to my kids, I say like, oh, we have this microwave. So there are waves, we put water, and in it, it boils the water. For fusion reactors, we also have some kind of magnetic waves, electromagnetic waves. So with electromagnetic waves, we can increase temperature. And actually, we have reactors now that successfully increase temperature for 150 million degrees of Celsius. So It's very challenging, but we can make it. And there are many questions. How? Because one question is like to increase this energy or this temperature. Another question is for reactor to be useful. So we have to keep this temperature for a very long time, and fusion, should be happening all the time, continuously. That's how we can extract energy. So that's a big challenge, and researchers, of course, are working on that.
Okay, so the idea with fusion is that the reaction should be self-maintained, like an eternity machine or something. Is that the long-term idea of it?
Exactly. It's like if you look to the surface of the sun, the reaction is happening forever. As from the day that sun was born, I don't know when. The reaction is happening, and it's keeping happening because the energy is produced by this constant reaction which is happening. So the idea with these fusion reactors that we want to build, we want to maintain fusion reaction inside this reactor such that this reaction should happen for a very long time. And only in that situation we can harvest like energy from that.
Okay. How do we then take that energy that the reactor creates and turn it into electricity?
Yeah, so in this fusion research, there are several really big questions. One of the questions is how to maintain the reaction. Since we said it's really hot, so 150 million degrees of Celsius, there is no wall material that can handle this type of temperature. So when we have a reactor, this reaction should happen in the core of the reactor without getting close to the boundary, to the walls. Otherwise, it just destroys it. Mm-hmm. That's one of the biggest challenges that people work, including I try to understand mathematical model for that problem. But the second challenge that you mentioned, how to harvest energy, because when the neutron releases and also a lot of energy releases, how do we gain it? For example, for fission reactors, we boil water and we create steam, and there is a propellers, and the propeller starts to rotate, and we get this energy. But so far for fusion reactors, we don't have a good solution how to harvest it. So there are some ideas, but these ideas is really vague because we have to solve the first question that we have: how to maintain and keep stable reactors. But of course, a bunch of researchers are still working now how to harvest energy from the reaction which is happening. But my research is not related on that part.
Okay. Is one idea to do it like we do with fission, that we boil water and then spin a turbine that generates electricity?
This is proposed, but think about that. water boils in 100 degrees of Celsius, right?
Yeah.
The reaction is happening for 150 million degrees of Celsius. So the idea when we ignite this reaction, so the fusion happens and it generates energy, and it should be self-maintained. So we don't need to send, magnetic waves to boil it anymore.
Okay.
So it should happen. It's like when you put a fire, you don't put fire all the time. Fire happens by itself.
Okay, so you guys have to just figure out how to ignite the system.
Yes.
And then it will be alive by its own.
Yeah, so related to your question, if you want to boil the water, it's 150 million degrees of Celsius. I mean, boiling of water, which is 100 Celsius, I mean, it's a bit challenge. But there are ideas. For example, they want to put some tube on these reactors. So the heat releases from that tube. You could probably build something on the connection to this reactor already, maybe with this boiling water, propellers, or even some factories that you can just use this heat directly. But
Okay.
we are not there yet.
Okay. Now my hobby expert mind starts spinning. Maybe they can use another type of liquid which has a higher boiling point or something. Maybe that would be an idea. But I guess the scientific community already is thinking about that. So, but it's just something I thought of now. So, who knows?
Could be. Yeah.
Before we go in with because I want to know more about your work with the simulations that you do. But before we leave this how fusion works thing, maybe you could explain and imagine that I'm one of your kids or students and I'm new to this. Could we just walk through how a fusion reactor would work step by step from the beginning in easy terms?
Yeah, in easy terms. So far, we have two types of reactors operating in the Earth. One is to create this pressure, as I said. So we have only one of that in Lawrence Livermore National Lab. And recently, by sending a lot of lasers in one point, they create, this pressure, high pressure. And also they increase the temperature and fusion happens. They actually made a breakthrough. What they got, the energy that they spent to this little small pellet to create this high pressure and temperature, after the fusion happened, it released more energy than the energy is spent to do this reaction. But this is just a prototype. We cannot create a reactor out of that unless there could be some reactors that, like a pulsating, you send waves, you create this high pressure, you release energy, you get it again, you send waves, and so on. So this is some kind of prototype that some people are, of course, thinking about that. But the second main idea that we have, it's called Tokamak reactor. Tokamak reactor, usually it has like a donut shape, and it is controlled by really strong magnetic coils. So all this boundary of this donut, if you think about the donut, so it is controlled with the magnetic coils. The idea is like we put fuel, like deuterium and tritium in between, it's like a gas. Then with the magnetic coils, we control that they should be at the center of this donut. So it shouldn't touch the wall of this donut, because if it touches, then we are failed. We are done.
Okay.
So then with the magnetic valve, we keep it inside. And the second way of controllers of magnetic, these coils is they increase the energy, the temperature. And we should maintain, as I said, really hot plasma in between, then fusion happens. And this is the second way that it's quite popular. We have some of the big projects like ITER in France. They are building the biggest tokamak reactor. We have some demo. It's called demo, this reactor. JET, we have it in UK. And we have another reactor in the US. People are working how to do that. So that's a basic idea how the reactor looks like and how should we create this energy.
Okay. And what was I going to say? These fusion reactors, we were talking about, um, it feels like the main challenge that they have is like material challenges, and
Uh,
that's a big obstacle. Is that correct?
yeah. So if I reformulate a little bit of your question,
Mm-hmm.
you may ask like, what are the challenges that holding us to create normal reactor which is operating now,
Yeah.
right? Something like this. So the physicists, of course, they work. This ITER project is international project. It's really big. Many countries, they are participating in this project. They even create a small town in France because they want to, unite all these scientists and try to solve this problem. So what is the problem, the main problem? Think about that. If we create this fusion, the plasma becomes so hot, it's more than 100 million of degrees of Celsius. We want to learn what is going on inside this plasma. So we want to understand like in what conditions we have a problem, because it shouldn't touch the boundary, right? The walls. So inside this, when fusion happens, inside this plasma, there are some instabilities try to happen. For example, if you boil water, water is still, but after boiling, you see that particles start to move really fast, right? So if you put a cover, then it actually, breaks your cover if you boil it for a long time. It's similar to fusion. When the reaction happens, there are so complex, behaviors starts to happen inside plasma. And in order to build normal reactors, first we have to understand what is going on inside plasma, like physical behaviors, all this stuff that is going on inside plasma. If you learn about those, instabilities, for example, all this turbulence, like there are some little shocks going on around. If we learn about that one, then we can predict it. For example, when we boil the water, we know that the water boils at 100 degrees of Celsius. We can control the temperature so that it doesn't boil and goes out from the pot, for example.
Yeah.
So, but in reality, we have reactors, not so many, but we have some reactors, but we don't have any device that measures this hot plasma. Imagine that we have thermometer, we put it and check our temperature, for example. But how do you measure all this physics which is happening inside plasma with so hot temperature, more than 100 million degrees of Celsius? So it's the biggest challenge that, applied physicists and engineering, they are facing. But what we can do, we can solve this problem through mathematical model. Because with the mathematical model, we can model this fusion, we can model this plasma. We have a well-established model. People are, contributing to the mathematical part for more than 100, 200 years. So we know quite many things. So what we can do, we can understand what happens in this high temperature, because for mathematics, it doesn't matter. If you increase temperature high or low, it doesn't matter. And we learn what is like physical problems happens inside this, fusion reactor. So with this way, with the help of mathematics and computation, because we have to solve it, these equations, we can predict and we can actually hopefully build a better reactor with the sustainable plasma inside.
Yeah, but how does this? It's one problem to simulate water and how water boils. I guess it's more simple. But how do you guys even create a mathematical model for fusion and the simulations of this? How is that even possible?
Yeah, so we go back for many, many years ago. For example, 200 years ago, there was first Euler proposed a mathematical model for fluid dynamics, so the behavior of water and fluid, for example. Then people started to improve this model. later Navier from France and Stokes from England, they improved this model and so on. For last like 200 years, we basically know how to model the movement of gas and fluid, for example. But what's the difference between plasma and gas? In plasma, the temperature is so high that in addition, every particle has electromagnetic field. So we have to take in account electromagnetic, behavior or interaction between each particles. So what happened, Maxwell, I think last century, he proposed how to model these electromagnetic fields which are on the particles. Yeah, there's a very famous equation, Maxwell's equations. And all these equations, so they combined Maxwell's equations with Euler's equations or Navier-Stokes equations. And they are really good model for plasma simulations. And of course, people are working, they're improving. How we make sure that this model is correct? We have to solve some realistic benchmarks, like easier one. And this part of validation is already done. So people are improving the model. People are also from the experimental science, they improve the benchmarks. So we have really good models that actually simulates plasma right now.
Okay.
So in that sense, I think we are quite in really good shape now.
Okay, so what you guys are basically doing is that you create these mathematical models and then you run some type of real life testing and then you compare those two results and then you tweak what you have to tweak on the model and that's how you evolve. Is that basically
yes,
what? Yeah.
Exactly. So the mathematical model should reproduce physical validations.
Okay.
So we have a lab, we have some physical experiments, we have a mathematical model. They should match. And this part of matching, how to improve the model, people have been working for so many years. So I'm not saying that the models that we have like 100% correct. We still don't understand many things, for example, for really hot plasma. That's part of the research in our field. Researchers are trying to improve the model. But the part that I work, I try to solve this model. Solving these mathematical problems is not easy. You cannot solve it with pen and paper. We try to solve it using computers.
Okay.
But using computers, our work is like we have to design some kind of like numerical approximation of these models because these are really complicated models. And we want to solve it. I mean, you see, like there was one challenge. There was a physical process. We made a mathematical model. There's a lot of questions like validation and stuff. The second challenge, how to solve this mathematical model. And my research is actually standing between this, how to solve the model and accurately.
Okay.
That's a question that we deal.
Okay, and to do all this computation, I guess you can't use a normal computer. I mean, what kind of computers are you guys using to simulate this?
Yeah, it's a good question. If we talk about these plasma simulations or fusion simulations, so far there are many models, of course. The most popular models are, one is fluid model. That's what I said, starting with Euler and Maxwell. For the fluid model, we solve for density. It is one equation. 3 equations for momentum equation, we solve it. 1 equation for energy, it's going to be 5. And 3 equations for the magnetic field. So there are 8 equations. It's very complicated, nonlinear. You cannot solve it with pen and paper. But now that's the 8 equation we want to solve. And if we want to simulate fusion reactor in 3D, you have to put a lot of points inside the model that we get it in the computer. So we create a model of reactor. We create a mesh. Mesh means that we put a lot of points inside, and we have to solve these 9 equations on the top of each point. And for accurate simulation, if you want to understand the physics inside this plasma, you need to have billions of points. And think about that, you cannot even fit in your laptop, so that is impossible. We have to use supercomputers. Like in Sweden, we have this Like in Uppsala, we have Tokamak Center. In Sweden, we have NICE Center that unites all the supercomputers in Sweden. So we have a project there. We are a member of that. We use our code there. So you see, one challenge was how to approximate this mathematical model. But another challenge, if we want to go to this computing, the model, the code that you write, it should actually work in big computers. You shouldn't think that, I will write little code which works in my laptop.
No.
So the level of thinking should be different. You have to aim directly from the beginning that your final product should be applied in these supercomputers and people should use it.
Okay. Would you say that computation speed at these supercomputers, or they kind of holding back your research and makes it slower? I mean, if there was supercomputers that were faster and can do more computations per second, would that lead you guys to solve the fusion question faster? Is that also a challenge?
It's a challenge. As I said, this couple of billion degrees of freedom that we try to solve, you cannot solve it in 1 hour. Probably even in supercomputers, it takes many, many hours, maybe even days. Mm-hmm. But when we design reactor, it should be, in runtime, because we don't say that, we see some behavior in the reactor. We don't say, turn off the reactor. I want to run my model to understand what will happen after this, because we can put it like initial condition to my model. I want to simulate in time, and I want to see that if some eruption happens, some instability happens. And this doesn't work, because if you ask me what will be the temperature tomorrow in Uppsala, for example, we have a mathematical model to predict temperature. So that's all this weather, forecast is people are doing with mathematical model. But it should be very fast. The correct model could take 2 days to predict temperature for tomorrow. If my model works 2 days, it's useless, isn't it?
Yeah.
So it is similar question for fusion research. So we want to have really fast computers, really fast models, but at the same time, the model should be mathematically correct, physically correct. So it's the biggest challenge.
Okay. Is the main, you could do real-time experiments with fusion reactors as well, but of course, if you simulate stuff, you can do more testing in a shorter period of time. Is that why we use simulation and mathematics, just to speed up? Like, instead of doing a reactor test for 10 days, with simulations, you can do, 1 million simulations.
Yeah.
That's the basic idea, yeah?
Yeah, the main idea with the simulations, we want to understand the physics inside plasma. For example, one of these biggest problem, it's called plasma. I put my hand, it's showing.
Yeah, I think it's a reaction from the MacBook.
From the MacBook, yeah. So one of the challenges, for example, is fusion eruption, it's called. When the temperature is very high, eruption happens. It's like volcanic eruptions. Then when eruption happens, inside, the fuel that you have, particles, they fly away to the boundary. Since the temperature is really hot, they just destroy the boundary. Because of that, we don't have experimental, result. Like recently, Chinese Tokamak reactor, they announced that they could hold this fusion reaction for more than 1,000 seconds, which is a record. So people ask but they are solving already your problem. Why do you need to model it mathematically if it is very expensive to solve it? I said, they did it 1,000 seconds, but they don't know yet how to make it 2,000 seconds.
No.
Why? Because they don't know the physics inside. We don't have any tools to measure and correctly predict these eruptions.
Okay.
But what we can do with mathematical models, we can understand in what situation, in what condition, in what temperature, on which level this eruption happens. So we do thousands of simulations and we learn ourselves the specific condition that eruption may happen.
Yeah.
And right now, people are integrating mathematical model that we do with machine learning. So the good thing with this, we can teach AI with the model that we develop. You can do it like passively, and the AI learns like all these situations, all the conditions that these instabilities, eruptions, all this stuff happens. And in real time, instead of solving, for several days, and in real time, machine can help you. For example, we want to control this, plasma with the magnetic fields. You can control, increase, decrease the magnetic, strengths, so that you can prevent these instabilities.
Okay. So what you guys basically are doing is to kind of put the laws of physics on paper so everybody can understand, and try to understand what's happening inside the reactor where we can't physically look or measure what's really going on.
Exactly. Physically, we cannot. We don't have any device physically go inside. Even with lasers, we don't have any good devices to see and physically follow what is happening inside. Okay. But we have a good model. But of course, the challenge here, your model, when you do this numerical approximation, you have to make sure that it converges to the right solution. You have to make sure that your numerical approximation also follows physical laws.
Yeah.
So that's a big challenge here. But once we have these, aspects, we solve all these questions, we use our model and we better understand the physics inside this plasma. And I'm sure that future Tokamak reactors or fusion reactors will be based on our model, like mathematical and numerical models, because this is the only way. We don't have any other devices to do it experimentally.
Okay. Wow, it's so interesting what you guys are doing. I wish I could work with something like that too. I mean,
you're welcome
kind of I'm not that smart, unfortunately.
Oh, really?
Just for my understanding, for plasma, is plasma a matter has what I think 3 states. It can be liquid, it can be solid, and it can be a gas.
Yeah.
Is plasma a 4th state of what do you call it? State of
matter. Yes,
matter,
it's a fourth state of.
Okay.
Yeah, because in addition to all this stuff, we have all the particles. They have a electromagnetic field.
Okay, because in school they always told us there's 3 states of matter, but there is actually 4.
The first one is plasma. Yes.
Okay, then I understand. Because you always hear plasma in video games and movies. You never know what plasma is like. Okay, so it's the 4th state of matter. Cool. Okay, but the model you guys are working at in Uppsala University, how do you think specifically that your model contributes to like the larger global effort?
Yeah, so I started to say there are 2 main mathematical models. One is based on fluid model. As I say, started from Euler, then Maxwell. And that's a good model people are using in other institutions. For example, in Germany, people are using quite a lot. In the US, many. So the challenge is like we just solve it in 3 dimensions and 9 equations. Here in Uppsala, we work also with that model. There was a PhD student working with us, and he successfully graduated. He contributed a lot on numerical simulation and mathematical aspect of that model. Then in Uppsala, we also work with a different model. It's called kinetic models. Kinetic model is started by Russian mathematician or physicist Vlasov in the 30s. Instead of solving for thermodynamic properties, for example, density, momentum, energy, in the kinetic model, Vlasov say that we want to solve and understand about the distribution of the mass. So the unknown is distribution function. The good thing with Vlasov model, it's only one equation, but because instead of 9 equations, you solve one equation. But the bad thing is this equation should be solved in 6 dimensions. So we live in 3 dimensions, right?
Yeah.
But that is solved in 6 dimensions. We have 3 spatial dimensions and we have 3 velocity dimensions because the model takes also the movement of the velocity as well. It makes really hard to solve it. And physicists believe that if you want to understand many physical properties inside plasma, kinetic model is a correct model. Because fluid model, it's a fluid model. It can predict and solve some of the features of the plasma, but kinetic model, since it goes to the particle level, it predicts and understands much more physics of the plasma. So in Uppsala, we work and develop both of the models. We have a code, we write this open source code. We make sure that it works in parallel computers. And this is part of the contribution that we do it in Uppsala. So the second part is when we do these numerical simulations, we have to make sure that, as I said earlier, our numerical solution follows physical laws. And so far, there are not, as far as I know, there are not numerical methods or mathematical model in other institutions. Maybe there are a few in some institution I can point it, that for sure, like with rigorous mathematical proof, says that the numerical approximation that they do follows physical models, physical laws properly. Mm-hmm. So I think I can tell that in Uppsala, we do one of the few centers that we propose new numerical methods and computational results that follows almost all the physical laws. So this is, I think, if you want to understand and build future fusion reactors, these models are needed. So I'm sure that in future, our contribution will be quite significant. We talk with other peoples. We talk with many people in Europe, including this ITER project in France. We collaborate with many people in the US, and I think we will do a significant contribution in the future.
I mean, you guys in Uppsala University, I've spoken to some of your colleagues in other subjects. With Ken Mattsson, he simulates like sound waves. And I've talked to other professors about nuclear energy. And you guys in Uppsala, it sounds like you know what you're talking about. You're really good, you guys, as far as I understand science. So
in Uppsala, we have one of the biggest scientific computing centers in Sweden. We are quite young in generations, including Professor Ken Mattsson. We are very active and we are covering quite wide range of computational science. So I think for future students, if they aim to learn this kind of subjects, I think Uppsala University is a good place to come.
Yeah, it feels also like you guys are more open-minded than traditional universities, because I've been speaking what is considered like controversial topics sometimes, and it feels like a lot of professors in Uppsala are more open-minded and can speak about stuff freely. So that's what I love. One thing that I love about Uppsala University. What was I gonna ask you? Do you sometimes feel like you're a physicist, a mathematician, or a software engineer, or all three at once?
Actually, this question I get quite often from many people. My education was pure mathematics when I did it in Tajikistan. I considered myself pure mathematician. When I came to Sweden, then I started to work with computational science, computational mathematics. Then I saw that, pure mathematics can be applied to real life, problems, and we can solve it now. Because in pure mathematics, usually the models we do, they are not applicable right now. Maybe they are applicable in 100 years, 200 years. Maybe we don't know yet. But in applied mathematics and computational science, we do something that is we solve the problems from industry and society now. So that's why it took my interest, and I pursued my education there, master and PhD, and also postdoc after that. And so when we enter to computational mathematics, then there are many, directions. One direction, you can do computational finance, for example. You can try to solve and understand all this financial stuff. The other direction could be like chemistry, computational chemistry. But the direction I picked, it was close to physics and fluid dynamics, thermodynamics, and now I'm doing this plasma physics. So when I started to do that direction, if you want to contribute something on that, you have to learn a lot about physics. So I'm not a physicist as a physicist, but I consider myself all three. I try to know some physics, I try to learn and continue learning mathematics and programming, because the computational mathematics, as I say it, the model that you have to write, it should be run in supercomputers.
Yeah.
So a computational scientist, I think you have to be as well. So all three in one, I would say.
Yeah. And I don't think is it like standard or normal for researchers like you to know all these three things, or is it more normal that you're one of these things?
Of course, it is normal for being a researcher. It is enough to know one of the directions and contribute. You have to invent something new which is needed for society. But I'm not saying that there are many people, of course, they are really good on all these three. But what I understood, if I want to contribute on this, science, on this topic for the society, I have to know all these three parts, because I have to control, my knowledge. I shouldn't rely on someone else, because when you rely on someone else, you can take the mistakes or bugs or all this stuff that they do it for granted, because you don't know it yourself. Mm. So I think if you want to contribute in computational physics direction, it's better that you know all these three aspects. You don't have to know it excellently with really high level, but you should know enough so that you come to some new idea. You should be yourself pushing your idea with all these three aspects.
Yeah.
So I think it is important to know all these three.
Good point.
Yeah.
And during your long research career, what is the most surprising result or insight that you have come across during all your years?
Yeah. So when I was doing my PhD at KTH, I was mostly working on compressible flow, flow with a high speed, for example. And we did some numerical simulation. We solved some interesting problem. Then I came to Texas, and I did my postdoc here. One of the discovery that we make here, we actually proposed a method that follows all the thermodynamics laws. So it was actually one of the unique methods that we invented in Texas. It was back in 2014. And many research papers and direction that we took it after that, it was mostly based on that one. Then it was for the high-speed aerodynamics I was working. Then I started to get interested on fusion problem and, plasma quite recently. What I say recently, maybe 5-6 years ago.
Okay.
6 years ago, I say that, okay, so I know enough knowledge about high-speed aerodynamics. As you say, this the third matter, which is gas. I know how to solve it. I know how to simulate it. It's very also needed for the industry. Then I say, if I move to plasma, to another matter, so can my model work for this plasma? And in that time, it didn't work, because plasma, it's a different matter. And in addition to fluid part, you have this magnetic field for every particles, which was really hard. You get additional constraint from physics, because there is called Gauss law. So this magnetic field, when you do this numerical simulation, it should follow Gauss law. And in addition, it should follow also thermodynamics law. So it was a big challenge. But together with the colleagues and students we had in Uppsala, we solved this problem for plasma. So a paper that we wrote it, I think, last year, it's one of the breakthrough in that field. I would say that it's a big contribution, and we are very proud of that. And now we are extending the same ideology for the kinetic model that I said is 6 dimensions. So I think there's a hope that we can do it also in that direction.
Wow, it's all very impressive, really. Dr. Murtazo, I was going to ask this before, but I think you have, could we look at some simulations maybe on the computer, if you can show us some of them? I think the people watching would love to see some cool models.
Yeah, I can show some of my recent simulations.
Yeah.
So I have some recent results. For example, since we are talking about plasma, I want to show a gas model when the magnetic field is 0. So we are not, on plasma level, but on compressible flow level. Then I will show the result when we include what is happening with plasma. So one of these simulations, and I think we did it. Now I have to open it with different. Open with VLC. So I can stop it here. It's just a numerical test. We want to solve this density, momentum, and energy I said, but the magnetic field I put it 0. So it's not hot enough. So we put some compressed gas inside here, and the level of compression is so high. So outside and inside, maybe the level of compression is maybe 10 times more. So when we open the boundary, the gas starts to expand because of the compression it released. Then it tries to heat these walls. So I put this wall. What's the purpose of this simulation? The purpose is like when we look to this inside plasma, there is a lot of instability starts to happen. We want to understand what type of instabilities are happening. And once we understand, then we know more about physics. And this is like a purpose of this simulation is just to show that what kind of instability can be modeled and can be seen also in reality. So when I start, it's going to be, you see the first wave that goes, it's called, these waves are shock waves. So there's a discontinuity on the density, pressure, and energy as well. But the second waves, these are like flower types, which also observed in physics. It's called contact waves, contact discontinuities. There is a discontinuity only on density. So it's surprisingly for this type of discontinuity, pressure is constant, velocity is constant, but only discontinuity is happening on density. So if you release, you see the shock waves, they get reflected, they get back. Shock waves is like a sound wave. You send it somewhere, it reflects and gets it back. And the good point of this simulation, it shows that the method that we are doing here, it's very accurate. Even after a long time, all these small instabilities, they are kept, and they are really well resolved.
Is this the donut-shaped reactor we were talking about before?
It is just a model. It's like the model, but if you think that about this inside the reactor, this kind of phenomena can happen.
Okay.
So I just want to test when I write my mathematical model and codes. I want to test what can I simulate. So these are just the benchmarks that mathematically we know what will happen, but this is numerically I want to make sure that I can resolve it. This small filament, because eruptions in the plasma, it actually happens from these filaments. So filaments, they join each other and the eruption happens. And with this way, we understand more how to model it.
What is filaments? Maybe a stupid question.
Filament, for example, you see this one. There is the density difference is high, so it goes when you smoke. The smoke which goes to the air is called filaments. So the smoke gets really long, and when it gets longer, it breaks down.
Okay.
So this is like something like
it's
that.
It's the density of the smoke.
Density of the smoke, which is like concentrated in really long path.
Okay.
And it breaks down and it creates another filament.
Yeah. The symmetry here is fascinating.
Symmetries, yeah, but if you look to the shock waves are symmetric. That is the theory also says. But the second waves, they are not symmetric. If you look to, if I start a bit earlier here, you see that the flower types, they are not symmetric because they shouldn't be symmetric. That's but these ones are shock waves. All the symmetrical stuff are shock waves. But I want to show something else about when we add, for example, magnetic field, like what is happening inside the reactor. So I do something similar here. So I plot magnetic field. So you see, I start from really like everything is smooth here. I just start and I run it. So there is a magnetic field is happening. There is a rotation as well. I want to understand what kind of like, so maybe let me just show another. This is much better quality, I think. So how it happens with the plasma when you have magnetic field as well. So you see, this is like a magnetic field I'm plotting. These are the filaments. So they are getting really stretched down. They are stretched down and they break down at some point. So that's what we want to understand and what we want to capture it. Once we understand, when we capture it, we resolve it, then this is like the physics we understand more. Under what conditions the filament happens and also shock waves happen.
Okay.
And what is the strength, what's the energy produced on these, filaments and so on. So that is another example. And I want to show something else with and without magnetic field. So I start, let's say that this is like a plasma, as you wish. So I put it in between, in the center. Then I just run it. But in this case, the temperature is not high. I just want to move the top one to the right and the bottom one to the left and try to see. So this is the density difference. Let's say that we are inside the center of Tokamak reactor, we put some plasma. I want to understand what kind of like instabilities that you get. You see this kind of instabilities that you get, it's typical for fluid flow and also gas dynamics and also plasma with low temperature because the magnetic field is not acting yet. And eventually it hits the boundary. So that's, we don't want to have it. We don't want to happen that plasma, after it gets unstable, it hits the boundary. So is it possible that we control it with somehow that boundary condition? Then I can show something like this, that here, in addition to the simulation, we have some magnetic, actions. And if you see, there's a magnetic field and the shape is quite different. It's more controlled.
Yeah.
So with this way, and also there are some filaments are releasing, but the energy of them are quite low.
Okay, so the more red, the more energy.
The more red is plasma is happening inside.
Okay.
And
so what you guys want to achieve is a more straight line and keep the plasma more under control.
There's a trade-off. If you put too much magnetic field on the boundary, this the red one will be straight.
Yeah.
So that is that we don't want that one either.
Okay, why not?
Because if it is straight, it doesn't generate energy. So
fusion, it's too standstill.
Yeah, it is like too strict. So
okay.
we want to have some flexibility, and also at the same time, we want to get control it. But this is just a benchmark how can we use magnetic field to control it.
Okay. So you guys want some kind of controlled chaos.
Something like this, yes. That is like at the end of the day, we want to do this optimal control. That is for sure.
And the simulation help you guys to, when you do the real-time experiments, it helps you to determine how much power you need for the magnets, how much volume you need to put the fuel in, and all other stuff, of course.
Exactly. So I can show you one more example. For example, here I have this plasma moving from the left to the right. I put the cylinder by purpose that I want to create some kind of instabilities. So I want to create some instability, then I want to control this instability. So if you do it now, on the boundary here, on the top and bottom, I want to put some magnetic field to control this instability. So in this simulation, you see I put B00. Z00 means that I don't put any magnetic. B is magnetic field. If you don't put any magnetic field, you get this type of instabilities in plasma, and it gets more and more chaotic. The idea that we want to control this one so that it is kept within some, some measurable stuff that we can control ourselves. Then I put some little magnetic field. I put 0 on that direction and 1 on that, 0.1 on the Y direction. And I run the same simulation, and you see here now that the wake, so instability, is more or less controlled. So for the previous one, it was a lot of fluctuating, right? With this one, there is, physics are happening, but it is controlled. And now if I go to even more, so I put 0.3, for example, here, magnetic field, and I get something like this. And this wake is fully controlled, so I don't see any instabilities.
No. And there's enough movement and action to create energy.
It could be. So there's a trade-off. You can put too much magnetic control, then probably nothing happens.
Okay.
You just
and when you say boundaries, do you mean the inside of the walls of the reactor?
Yes. For example, on the reactors, there are these magnetic coils, right?
Yeah.
So magnetic coils generate magnetic fields.
Yeah.
And when I say boundary, it's the amount of magnetic field that every coil generates.
Okay.
So here, for example, I put like uniform magnetic force in all these boundary points, right? But what you can design in the reactors, you don't have to put uniform. You can just play it like a music. So one part of the coils, they increase, magnetic field. The other part, decrease, and they control. So because this reaction should happen inside.
Mm-hmm.
So because if you put uniform, really high magnetic field, then you just kill the reaction. I mean, reaction doesn't happen.
No.
But you have to give some flexibility. It's like flame is flaming, right? Burning, right? And also you have to control with some really smart way. Okay. These magnetic coils that, it keeps it stable inside the reactor.
Okay. And have I understood it correctly if that the function or the reason for the boundaries and the magnetic control is the reason for the plasma not destroying the reactor from within to keep it from the walls? It's that the main function?
Yes, it's one of the main function, exactly. Because we can create a fusion just out of nothing. But the role of these magnetic coils, that's why these devices are called magnetic control device, magnetic confinement device.
Okay.
Because we want to control plasma with this magnetic. And so, as I said, like in practice, it's very hard. Did I stop my screen?
Yeah.
Yeah. So in practice, it's very hard to do it because we don't know in really extreme situation, we don't know the physical, properties of the plasma. But with the numerics, we can, reproduce this plasma simulation as I showed it here with some examples. Then we can learn the magnetic coils. So we can design an optimal control for the magnetic coils such that the plasma is controlled and energy is, produced significantly large.
Okay.
And how to do that? There's a mathematical model direction. It's called optimal control. So they do really complicated. You have I give the solution. There's a model that uses my solution and designs optimal control for the magnetic fields. But that is really expensive. It's very mathematically sound, but it's very expensive.
Okay.
And right now, some people are using AI for that. Maybe because you can train AI and use it like in real life simulations.
Okay. So is everyone trying to find that spot where the control of the plasma is just enough to create like net energy and spare the reactor from being damaged? Is that the sweet spot you guys are looking for?
Exactly. That is a biggest challenge that we are trying to deal.
Okay.
Once we solve this, I think it's going to be a big.
Then we have fusion.
Yeah.
But one thing with AI, I mean, AI can do a lot, but we still have the problem we talked before about the computing power. I mean, a processor can only manage an amount of computations per second, then it can't do anymore.
Mm-hmm.
Have we come far enough with quantum computing, for example? Is that something that is used, or is it too far away?
Quantum computing is far away, but if you have quantum computing, of course, it helps it a lot.
Okay.
Because as I said, for this optimal control part, it's if you make it really mathematical sound without using AI, because AI doesn't follow any mathematics, then you need something. You need quantum computing to make it the computation fast and decision making really like in real life, real time.
Has there been any talks with you guys on your field and with quantum computing fields? Has there been any like talks or?
Yeah, there are researchers in Uppsala. They are trying to investigate quantum computing. But for quantum computing, there are specific algorithms that you have to design your method.
Okay.
According to the algorithm that they give. But I think I have enough problems to deal, so I'm just.
You can't do that as well. It's too much.
No, it is. Wow. I think it's. For the time being, I just want to focus on the problems that I told you.
Yeah. Well, it's very impressive. I've learned so much. I tried to research a bit before our conversation today about fusion, and now to talk to you and seeing the simulations and really understand the challenges is really eye-opening, because I've watched some videos on YouTube, but they're more commercial. They don't explain in depth, so talking to somebody who works with it and researches it and it's really good at it, it's really eye-opening, and it's really nice actually. But one thing I wanted to mention to hear your thoughts about it is I've been talking to some other professors that mainly works with fission. They're physicists and professors, and they kind of they joke a little bit, but I don't know if they joke or they're serious. They say sometimes that fusion is always 30 years away. Do you think there's something in that, or will we see fusion working sooner than 30 years?
Yeah. When this fusion research started many years ago, maybe around 80s, the estimated time was 30 years. Okay. And it is still 30 years, and I'm sure that it will take probably more than 30 years. But why do we always promise 30 years? Because based on the knowledge that we had at that time, we can estimate that it can be in 30 years. I mean, it started since the 80s. We couldn't build a reactor, which works produces energy. But we learned a lot. So a lot of breakthrough in this research field was done. And it would be impossible if we wouldn't put this 30 years aim in the 80s and go to that direction. And for example, this fusion reactors that we have that keeps the reaction 1,000 seconds, it's a breakthrough. So nobody thought in the 80s that it was possible.
Mm-hmm.
Right now it is possible. And also this net energy produced with the pellet, which was done in Lawrence Livermore lab. People thought it was impossible, but it is possible. We can do it now. And the good thing with this fusion research now is many commercial, sites, they are also interested. They try to build their own, reactors. We have it in Stockholm. There is a Novatron Fusion. It's a startup company. They have an interesting idea to design a new, different type of fusion reactor.
Mm-hmm.
And they have a goal to build some small reactor. So since the private sector is interested and people start to invest, I'm sure that it will be happening pretty soon, even in many years. Of course, we are behind. Okay. So I think there's a point, and I think we have a lot of discoveries, and I think we are in good shape to make it happen in the near future.
Okay. What was the company called in Stockholm?
It's called Novatron Fusion. We were also in contact with them, and hopefully the final product that we are developing, we will test it in the geometry that they are developing. So this is
cool. I actually think you guys gonna solve this fusion problem sooner, because if you look at other technological fields, technology is usually exponential. So 100 years ago, we had basically no electronics. And just 100 years later, it's, we can sit here and talk. You sit in Texas, I sit here in Sweden, and we're close to breaking fusion. And so I think also this will be exponential, this field that you are working with. So I'm more positive, actually.
I agree. And also this computational power that we have it now.
Yeah.
In the 80s, we didn't have these supercomputers. Now we have a computation. We have more tools. I agree with you. Yeah. And the governments are also investing quite a lot. Yeah. If you take this ITER project in France, the budget of this project is around 60 billion euros.
Yeah.
So I think there is an interest, and it will hopefully happen sooner than later.
Yeah, because I hope so, because I'm a big fan of fission nuclear power, because like one professor said, he said it's not the best way of making energy. He said it's the least bad way to make energy. So it's the best solution we have today. But like you mentioned in the beginning, there's always risk with fission. You have the radioactive waste, you have the risk of it exploding. I mean, the new power plants are pretty safe, but it's still, you never know. Anything can happen. It can be bombed. You can have an earthquake. In Japan, we had Fukushima, which was hit by 2 tsunami waves, I think, but it managed anyway. So there's a lot of risk. And with fusion, I don't think there's the same risk. No. The research I did said that if the nuclear reactor fails, then it dies out by itself. So there's no explosion.
You turn off and you are done. You go home.
Yeah. So that's a good part.
Yeah.
But what do you think, just a final question here, your vision, if fusion becomes reality, what do you think then the world will look like from 50 years from now or something?
50 years from now. So I read a lot of these energy reports. Right now, fossil energy, for example, burning gas, oil, we still use it a lot, like 80% of our daily energy based on fossil energy. And this projection in 50 years, it will not decrease significantly. It's going to be 70%. So you see, we will just burn out everything. And in addition, we just destroy atmosphere. I mean, all this global warming, it's in our hand. But also in another direction, so access to energy is one of the fundamental need of humanity. So since humanity understood each other, we need to get access to energy. Because when we have unlimited access to energy, we can solve many problems like food crisis. I'm sure it will be solved.
Yeah.
So in 50 years, if we get access to fusion and we have many reactors which is producing, unlimited amount of energy because we have unlimited source for that one. First of all, the life quality will be completely different. We just eliminate poverty because we produce so much food and education and all this technological stuff that humanity will not suffer anymore. And hopefully all this, conflict and stuff, it will be there will be probably some conflict anyways, but it will be gone. And the level of this energy, access to unlimited energy, will give us really big boost on industry. So industry will be developing, technology will be developing so far. So we will not be limited in the earth. We will just go to the sky. We just, go to Mars because we have a source of energy in Mars to create and do some kind of, food and all these technological stuffs there. Mm. So I think it's going to be life-changing. The life quality will be completely different. All this, we will just fly away from the Earth and start to discover, universe. And I think it will happen. This will open a new direction for humanity. Think about that. When electricity was invented, it was a one big direction for humanity. Fusion energy, it will open completely different direction. So I think and hopefully we will see it.
I hope so too. It sounded very positive, and I hope the world comes to that point. But I'm a bit negative and maybe pessimistic person, so I think that somebody will come and patent technology and control it and still charge us for using it. Like it's a capitalist globalist world we live in. So I hope I'm wrong. Absolutely, but
you could be right because private sectors are investing now, but public sectors. I told you about this ITER project. Is like European and world project in France. It's from our money. It's like taxpayers' money are paying for that budget. Yeah. If it happens, it's going to be for the good of all humanity. Hopefully, nobody will just patent and sell it.
I hope so. Well, Dr. Murtazo, thank you once more for joining us and educating us. I'm certainly more educated now than I was an hour ago. So I hope my questions could keep up with the level of knowledge that you have. It's always challenging to sit here with a professor or a doctor or whatever to talk about this complex stuff, but I try to keep up. And thank you once again for joining us.
Thank you so much for the invitation, and I hope we had a good discussion about this direction. And I just want to finish with some words that researchers are always positive. We are positive. We want to aim for the future. When we even write a grant, we aim for the good future, and we try to achieve that aim. And also in terms of like education of young generations, I think we can influence, and your podcast can influence some young generations that they can choose the direction they want to pursue in education and life.
Yeah.
By deciding for good future, they should be positive in life. They should be positive on what we are, creating, and they should contribute it. And I think it's going to be hopefully in that direction. And thanks a lot for the invitation. I was very happy.
Yeah, of course. It's an honor. It's my pleasure. I mean, I hope that some young people see this, some students, and they get interest in the subject and try to solve this and maybe start studying this field, because it feels like this new generation, they only want to be like TikTok famous or social media famous, and there's not so much interest maybe in science and technology. So I think we have to make it cool somehow, make it trending and stuff like this. So I hope people listening can choose this path to education and hopefully solve the fusion problem. someday.
Yeah, hopefully. Yeah, we need help.
Hopefully.
Always we need help.
Yeah, and best of luck to you and the research, and you're welcome once again to talk about this stuff. So
thank you so much. It was my pleasure to be here.
Thanks.